Hello, Mia. So, I talked with your mom a long time ago now about the fact that when you change schools, especially in the middle of the year, there's a potential that you miss some topics. So, an example of what I mean is that we could do things in different orders. So, say our first topic of the year is, since we're going to be talking about exponents and indices, let's say that's our first topic of the year. But maybe because you were going to school elsewhere, maybe you guys started with totally different ideas. Like, for example, exponents and indices start out as a number idea and then they move into an algebra idea. But maybe you started the year with geometry. I don't know. So then you did geometry maybe in your old school, and we did algebra or number. And then when you transferred, we haven't done geometry yet. So there's a potential that you get topics double, but that also means you miss some other topics. And we wanted to make sure this doesn't happen. Two of the topics that when I talked with your mom, she was saying you haven't had like a formal lesson in exponents and indices or in square roots and surds. Those are things we did earlier in the year. And so I want to give you just some short little mini lessons on these. And I'm just going to give you, I forget if there's like 4 or 6 problems to try of each. And if they go well, then great. If they don't go well, then I'd love to talk about it and give you some more problems and make sure that you get proficient with those ideas because we covered them earlier in the year. The area of model of multiplication, we actually had covered earlier in the year, but since it took me so long to do this video, you actually have already shown proficiency in this. So I pulled some of your work for the area model of multiplication, and I want to look at it and show where you've really nailed this topic, and then one place where maybe we could improve your ideas of the area model. The multiplication itself, you are a rock star at, but the area model, maybe we can improve your understanding. I'm not sure. And then the last topic is the Civ of Eratosthenes. Civ of Eratosthenes is really interesting, but in terms of a topic, it's much less important. So I'd like to just be clear. The really important things here are the first 3 topics. And the first 2 topics are the ones that I'm not sure if you've ever been introduced to them before. From what I've seen of you so far, you've been a fantastic student. So I have no doubt you'll pick these up really quickly. And they're not terribly difficult, especially at the 6th grade level. I don't think you'll have any troubles. Yeah, that said, let's get started. So my first mini lesson for you is going to lead up to exponents and indices, but it requires some history. So humans developed the ideas of numbers with a specific like building on previous ideas, like a specific process. That's the word I was looking for. So the earliest humans, or possibly even pre-humans, like before we were even Homo sapiens, we think people had already developed the idea of a successor, which is really the idea of counting. It's the idea that a number has another number that follows. So originally it was just vocabulary. We have the ideas of 1 and 2 and then many. This was common in primitive languages. They would literally only have the words for 1 and 2, and beyond that, they would just say many. So then if you were bartering in the market and you wanted to barter away, whatever, 1 pig to get 10 of another item, well, counting out those 10 items could have been difficult because humans were so primitive. I mean, this is obviously a long, long time ago. The earliest humans are pre-humans. But they had an idea that like 2 follows 1. So 2 is the successor of 1. And they had an idea that there was a successor of 2 and a successor of that number. It's just originally we didn't have names for all of those. By the way, there is a lot of evidence to suggest that animals can also count in this way. Crows specifically are very intelligent, and there's evidence to think that crows can count at least to 4 and maybe to more than that. But then they would basically have the idea of 1, 2, 3, 4, and then many. So next, after these words, many cultures had many numbering systems. So you've actually learned one of these numbering systems. I'm sure you've learned Roman numerals. Roman numerals is a number system and not a terribly great one. But at the time when the Romans were using numerals like this, there were not many cultures in the world that were using standardized numbering systems. So it actually was fairly innovative at that time in the world. So the problem is we have many cultures with many numbering systems. So if we use this numbering system and then we travel to somewhere that doesn't have it, all of a sudden we have communication problems. This was common in the Greek Empire. I don't know how much you know, but the Greeks were city-states who were all separated from each other. which means in Athens, maybe you have one numbering system, but then you travel to Sparta and they might have a totally different numbering system, which means it's really, really difficult to do business. So the next step was Fibonacci. Fibonacci, I think maybe should have two C's. No, maybe I'm right. Fibonacci was a really, really important person in history, probably the most important mathematician between the years, like, I'll say the years 200 and 1500. He was probably the most important mathematician. What he really did was write a book. Fibonacci was a mathematician that traded along the Silk Road, meaning he went from Europe over to China and then back to Europe. And he learned a lot of things from traveling so much. One of those was Indo-Arabic numbers. So Indo-Arabic numbers are named such because they came from India and Arabia, which is now kind of the Middle East on over to India. So not quite the Far East, but stretching that whole section of the continent. Traveling there, Fibonacci learned about these numbers and he was like, dude, this is smart. So he basically wrote a book that used these numbers and published that book, and it was massively wide selling. Wide selling in the year, I don't know exactly what year, but around the year, whatever, maybe 800 or 1000 there aren't that many literate people. But people were buying this book because this was such an awesome idea to just say, like, why don't we all use the same numbers? So first we had successors, the idea that if we have a number, there always is a successor, and every number has a successor. If I tell you what number comes after 11, you immediately know it's 12 because that's the successor. The next step in human history after we have, common numbers that everyone is using is we end up with groups of successors. So if we have groups of successors, if I have 3 ones and I want to add that to 7 ones, well, we get the idea that we can use successors and count on and go 8, 9, 10, which gives us 10. But eventually people start putting together that this is just an additive process. We've now created the new operation of addition, and we don't need to go back to these ideas. We can just add things. So successors came first, then came the idea of addition, which is adding groups of successors. In this case, I'm taking this group of 3 successors and this group of 7 successors, and when I put them together, we get this group of 10 successors. Great. The next step after that was people realized when we have additions going on and we're using these additions to do important things, then a lot of the times we end up with lots of similar additions. Like I end up doing 4 plus 4 plus 4, and that's annoying when we have lots of groups of equal additions. Equal additions because they're all 4s, additions because we're adding equal groups. So instead, people realize we can just know repeated addition creates this new operation of multiplication. And now that we understand the way multiplication works, we don't need to do repeated addition. We can just understand this new process. Great. That begs the question for where you are in mathematics, however. What about groups of equal multiplications? So if I had, instead of adding 4s, if I had 4 times 4 times 4, well, this is even more annoying than the additions because it's more difficult. Like 4 times 4 is 16. 16 times 4 is not so difficult, but these numbers get very big very quickly. So it'd be nice if we had a way to deal with equal multiplications with a nicer notation than this. The answer to that notation is exponents or indices. Exponents is common to say in the Americas, I'll just say AM, and indices is common to say in the UK and in places that use like UK similar language. So if you hear of an index, we're talking more UK style. If you hear exponents, we're talking more of an American style. But what they refer to is groups of equal multiplications. So say I had that 4 times 4 times 4. We want a way to write this in a nicer way that just describes the same thing. So in this case, there are 3 4s that are multiplying. The notation that was settled on is saying 4 to the 3rd power, or 4 cubed. So I'd like to just write that real quick, and then we'll look at some vocab. 4 to the 3rd power, or 4 cubed. There are only a few exponents that have these special names, and so you have to know really 2 of them. The 2nd power is squared, the 3rd power is cubed, and those are really the only ones you have to know. Other than that, we say 4 to the 4th power, 4 to the 5th power, or for example, This could be 2 to the third power, or it could be 2 cubed. Both of those would be fine. So for the vocab of indices and exponents, up here we have an index or an exponent, and that index tells us the number of times we multiply the base. So this 2 is the base, and if I wanted to know what this thing means, I would say 2 is the base, and then 3 tells me the number of times to multiply that base. So I could go ahead and simplify this and get 8, but that's not my point here, and 8 because 2 times 2 is 4, and then 4 times 2 makes 8. But my purpose here is really just the vocab. So we have an index or an exponent that's up here. We have a base that's the big number. It's the thing that's multiplying over and over. And the whole thing together is called a power. To be honest, indices and powers are used interchangeably. So like you heard it earlier when I say here, this is 2 to the third power. Well, that means this 3 is a power, and we say that often. We call it a power. Technically, it's an index or an exponent, and the whole thing is a power. But I'm just saying those words get used interchangeably all the time, even though there is a technical difference. So given this brief explanation, I'm willing to bet you can go ahead and try out page 19, practice 3, number 2. Your mom had found the book online, so I think you have that page, but if you need it, absolutely let me know and I will send it to you. I think there's only 4 problems or so. When you're done with them, you're absolutely welcome to send me your solutions and I'll check over them, or you can check your solutions with your parents. These are not terribly difficult, and I'm really willing to bet you'll just blow through them. So great, that's kind of the end of this mini lesson. If you want to try those out and then come back when you're done, we'll get to the next mini lesson. Well, welcome back, Leah. I'm assuming that you've tried out these problems and either sent them to me or checked with your parents, and you feel pretty good about indices and exponents. So we have some new vocab, some new ideas about the way numbers developed, and you probably feel pretty good. If not, let me know. If you're feeling good, let's go. So in order to talk about our next topic, we need to get the idea of inverses. I want you to think of inverses as opposites, but I want to expand your idea of what opposites are. When we say opposites, people almost always think of additive inverses. So these truly are opposites. Just meaning people are correct to make that connection, but we can cancel things out. Like the reason these are opposite is they cancel out with addition. If I have 5 plus -5, those things cancel out and make 0, which is why they're opposites, which is why they're inverses. So we can also cancel out with respect to multiplication. So we have multiplicative inverses, because if I take objects like these, 2 times 1/2, those things also cancel out, but they cancel out differently in multiplication to make 1. You may have been taught to make this 2 over 1, which is fine. We could cancel those 1s or say 1 divided by 1 is 1. It doesn't really matter how we think about that, other than the fact that the 2's cancel and what's left is 1. So things cancel with respect to multiplication. We call those reciprocals. So technically, additive inverses are opposites. Multiplicative inverses are reciprocals. So that's another vocab word. Reciprocals are pretty easy to come up with because we have the idea that things cancel when we have one of those numbers on top and the other one on bottom. It literally comes out because 2 divided by 2 makes 1, and so they just go away because it's a times 1. So reciprocals, if we want to find things that will cancel, let's say we had a difficult fraction like 3/5, and we want to know what will cancel with that to make 1. Well, all you need to know is that we need to cancel the 3, so we put 1 there. We need to cancel the 5, so we put 1 up here. 3 divided by 3 is 1, those go away. 5 divided by 5 is 1, those go away. And what we're left with is 1. So this is the idea of inverses, or how things cancel. Inverses undo each other. So 5 and -5 undo each other and make 0. 2 and 1/2 undo each other and make 1. But now we have this new idea of indices and exponents, and we should be able to cancel out or have opposites or things that cancel in respect to inverses and indices as well. I'll be honest before I start this is kind of part of the story, but you won't get the rest of the story for several years in mathematics. Eventually you'll talk about something that is relatively complex called logarithms, and that's the true answer to inverses of indices. I shouldn't write it because my handwriting is terrible. So I'll say the true inverse is logarithms, but you don't need to know logarithms for a long time. So for now, I'm just going to cross that out and leave it on the side and say, don't worry about it. But we do need to think about undoing indices. So how could we undo indices? Well, when you did the assignment, you had said things like 4 to the third power is 64, which means we should have 64, and then we can do some things and get back to 4, because that would be undoing, like this one took 4 and went to 64. If we had stuff here, we'd be starting at 64, undoing the things and getting back to 4. Here's the way it looks. What we call those, the inverse in this case, are surds. So surds are, again, this is a very British, or also I'll say UK, they call things surds. In America, we call things square roots. They're the same thing. So they're both just words you need to know. And what they do is they cancel out exponents or indices. So if I had, let's say 3 squared becomes 9. The notation we use is strange, but we know we want to have 9, we want to do some things, and in the end we want to get 3. The way the notation looks is we put this bracket guy on it. This bracket has a name, so I guess I'll put it over here. Bracket is called the radical. Radical, or surd. So again, this is like an American versus British thing, but yeah, radicals. What's strange in a radical, well, I guess before I say what's strange, we also could have 3 cubed. 3 cubed would be 9 times 3, which is 27, meaning we should have another type of thing that I can start at 27 and get back to 3. What that looks is we use that same radical, but we put a 3 here, just to say this is the cube root, or the third surd, the third radical of 27 gets us back to 3 because it's the inverse of this. What's strange that means with the square root is we do not write this 2 that's in front there, but there is an invisible 2 that's in there. If there's nothing written there, then it is always a square root, and you're looking to cancel out like a squared. So you're thinking, what squared makes 9? 3. Whereas here there's a 3 filled in, so now it's not squared. We're thinking, what cubed makes 27? And in the end, it's 3 in this case. So I'm willing to bet that's enough that you could try out page 19, practice 3, number 3. I think, again, it's only 4 or 6 problems, and I'm willing to bet you'll blow through it. But check your answers with your parents, or you can email them to me, and I would love to check them out and let you know how things are going. So this is kind of the end of the second mini lesson with one thing I wanted to say. We noted there's an invisible 2 here, and I wanted to say this is the only invisible 2 in mathematics. Given any number, if we have a 4, we have an invisible 1, because that's times 1. We have an invisible 0, because I can add 0 to it. So I don't need to write those things, but those things are there. We have a times 1 and a plus 0, which means we have invisible 1s and 0s all over the place. This is the only invisible 2 in all of mathematics. So you just have to know that it exists. Once you've tried those problems, come back and push play, and we'll go to the third topic. Welcome back, Leah. So here is our third topic, the area model multiplication. I just clipped in your work here because you showed a great proficiency with how to compute these. You knew 3/4 times 1/2. This is 3 out of the 4. This is 1 out of the 2. Overall, I can see you counted 3 out of the 8 total, so we get 3 out of 8. Or 3 out of 8 units squared. Great, I didn't even expect units squared, but I agree with you. These ones are perfect in the same way. This one, what you've done over here is perfect, and I totally agree with it, but I think we might be able to add to your understanding because we can do this problem using the area model and not using algebra the way you did, even though your algebra is perfect. So what I'm thinking, if we're going to use the area model, I know we're going to get 12/35 in the end, and one side measures 4/7. So I'll start very, very similarly to what you did. No, I'll use straight lines because my handwriting is really bad. So I'll start the same way you did. We have this box, and in that box, I know I want to make 4/7. So if I'm going to make 4/7, I need to cut this into 7 pieces, and you are actually really good at this. 7 pieces is pretty difficult. So that's 2, 3, 4, 5, 6, 7. Those are like, I don't know, kind of decent. They're not perfect. So we end up, oh geez, sorry. We end up with something like this, and I'm sorry, but I don't want to waste your time, so I'm trying to go fast. Okay, so you have the idea, you absolutely know. That's 2, that's 4 out of the 7. So we're looking at those 4. And then what do we need on the side in order to make 12 out of 35? Well, I know it is out of 35. So when I look here, we have 7 pieces. If I want to make 35, I better have 5 pieces because it's 5 times 7. So that means on the side here, I need 2, 3, 4, 5. And that lets me fill in the rest of this array. And I know we're in these 4 columns, and we want to end up with 12 of those. So if I have 4 columns here, and I need 12 total, that means I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I can then look on the side here and I can see this has to be 3 out of 5, which is exactly what you got. I see this. It should be units, not units squared, because this is just the side. But I just wanted to note that while your algebra is perfect, we could use the area model to do the exact same things. Area models for multiplication are huge. And I'll be honest, the reason is right now we're multiplying and dividing, like in this case, we were dividing objects that are like somewhat complex. Fractions are definitely complex to a certain level, but soon we'll be adding, multiplying and dividing algebraic objects. And when we remove all the numbers and things become algebra, it's way harder for students. So I want to use the area model to support your understanding, because when this stuff becomes super difficult because the numbers will become algebraic, this stuff will always look identical because this stuff is just an area model. So I just want you to be proficient with it, and you showed great aptitude here, and I wanted to move you forward here. Good. I don't really have more practice problems for you. If you want to, they're easy to make up. I mean, just choose problems. And if you want to, you could also ask me. I'm more than willing to make up some. But I saw you were pretty proficient here, so I don't think you really need more practice. I think you will fall right in with where people are in the class and understanding. So this is my third topic, and you can go ahead and like pause the video if you're done with this for now. But I'll go to the fourth topic next. So welcome back, Leah. My last topic is the sieve of Eratosthenes. So again, we need a little bit of history to set this up. So let's get some history going. The Greek mathematicians, I talked a little bit about the Greeks earlier. The Greeks were, math has had a few golden periods in history that just there have been a few hundred years, all of this math is created. And then we go for hundreds and hundreds of years with nothing being done. And the Greeks were one of the first really great golden periods of mathematics, is why we go back to them. So they defined the first written mathematics. This is somewhat of a stretch. The Egyptians also wrote down mathematics, but the Egyptians solved one problem at a time, and the Greeks generalized and solved entire classes of problems. So they would solve one problem that can be applied to 1,000 different problems, if that makes sense. They discovered the 4 great problems of antiquity. These are interesting problems because they are problems that went for almost 2,000 years without being solved. So these 4 great problems were defined by the Greeks around like the year 0 CE. Yeah, they were defined by the Greeks and then not solved until René Descartes. So René Descartes, you've probably heard, I think, therefore I am, is René Descartes, but he actually did a lot of really astounding mathematics. And one of the things he did is solve the 4 great problems of antiquity. One of them dealt with finding prime numbers. So we need to talk about prime numbers quickly. I would expect you already know these, but if you don't, then we'll do it now. Prime numbers are numbers with exactly 2 factors, and factors are multiplying objects. So if I'm looking for prime numbers, I want numbers that only have 2 numbers that multiply into them. So let's look at a couple numbers. What if I look at the number 6? Well, what numbers multiply into 6? 6 can be 1 times 6. 6 can also be 2 times 3. So right there, I have 1, 2, 3, 4 factors, which tell us that 6 is not prime. The other word, the word for things that are not prime is composite, but prime is a far more important word than composite. So they're both useful to know. 6 is composite, just meaning it is not prime. Let's look at another number. What if we looked at 11? The number 11 can be 1 times 11. It could be 2 times 5.5, but 5.5 is not an integer, so we don't count it in the same way. So that means if we take out those decimals, 1 times 11 is the only way we can make 11, and that's it. So what that means for 11 is that 11 is prime. Given that, I bet you know a bunch of primes, so you could try to list them off. I guess, why not? Try to list some primes that you know, like the first primes, and then come back and push play, and we'll see if you got the same primes I did. So I'm assuming you just use this idea to list out some primes. Here are the first primes that you could have listed out. Primes are things like, we've got 2, we've got 3, we've got 5, we've got 7, 11, 13, 17, 19, 23. These are all prime numbers. 29, and so on. A lot of students want to put 1 here, but if you notice, my definition of prime is we have 2 factors. 1 is only 1 times 1. It only has 1 factor, so it falls apart. It also does interesting things, so I just want to note 1 is actually not prime because it's a special thing called an identity. The other identity is 0. 1 is an identity for multiplication. 0 is an identity for addition. You don't really need to know identity yet. You do need to know what prime numbers are, and 1 is not a prime. So, good. Now that we know prime numbers, let's talk about Eratosthenes a second. He is one of my favorite mathematicians. He's brilliant, brilliant Greek mathematician, and the first person to accurately conjecture, like a conjecture is a well-founded guess based on evidence and logic. He conjectured about the circumference of the Earth, or the distance around the Earth, and he was very, very close. So it's pretty cool and interesting the way he did it. I don't want to spend a ton of time because I don't want to waste your time, but it's interesting. Eratosthenes knew the Earth was curved, which was already pretty fantastic and interesting at the time. And he, on one day, let's say it was like the summer solstice, June 21st, I think. I hope that's right. I forget what city he was from. I should know that. Yeah, I forget. Let's say he's here on the Earth, somewhere in the northern hemisphere. And on that day, he measured the sun comes in straight, if I can draw it, and he measured looking down into a well. He measured when does the sunlight go straight down into that well? And he had some time of day, whatever that is. Then later on, like another year, on the same day, he was in a different location on the Earth. Like he traveled to, I think one of them was in Alexandria, and measured the exact same thing. And what he saw is in Alexandria, or wherever the other city was, we had different times of day for these things. Those different times of day define how far apart these are, and he knew he could measure the distance between the cities. So then he knew that distance, like that proportion, is one part of the entire way around the circle. He multiplied it out, guessed the circumference, and he was astoundingly close. So hopefully this gives you an idea of how brilliant this guy was. But here's where I really want to get at with primes. He worked on the problem of primes, and he developed an algorithm that will find all of the primes. So an algorithm is a series of steps that complete a process. So you could write an algorithm for brushing your teeth, and it would say things like, step 1, pick up the toothbrush. Step 2, put toothpaste on the toothbrush. Step 3, brush the toothpaste against all of your teeth vigorously for 30 seconds or whatever. I guess 30 seconds is short. I think you brush your teeth for 2 minutes. That said, an algorithm gives you steps. It says, step 1, pick up the toothbrush. Step 2, put toothpaste on the toothbrush. Step 3, do something else. So it gives steps. Textbook page 20 will walk you through the steps of the sieve of Eratosthenes. And I hope when you work through that, you should see all of the primes would pop out when you did this. The last thing I want to tell you, finding primes is a very, very difficult problem, and a problem that had no application for thousands of years. So Eratosthenes and the Greeks worked on this problem even though you couldn't do anything with it. It was just fun. Like it was basically, instead of going to a movie, they would be like, hey, let's sit down and chat about primes for a while. Obviously, movies didn't exist then. So that's the idea of what Eratosthenes was doing. He created a series of steps. They give all the primes. Oh, that's where I was going. Sorry. If you found a way to effectively find all of the primes, I promise you, you would win millions of dollars. I could point you to several websites that would pay you out 1 million each. And the reason is that primes went for 2,000 years without an application, but now they're the basis of internet security. And they have all of these computer programming applications. So people are always looking for new primes. And you would be a millionaire even if you found one new prime number, then you would be a millionaire. So it just tells you this is a difficult problem. The sieve of Eratosthenes works, but it works very, very slowly. And you'll see that when you work through that. I'm talking too much. So thanks a lot. Best of luck, Leah. If you want to send me your work on this, that's great. Or if you want to check in with your parents also, that's totally fine. So try it out. Let me know how things go. And I'd love to chat with you soon. Thanks, Leah. Have a great day.